Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Privacy attacks are attempts to learn sensitive information about people or records by observing how an artificial intelligence system behaves. Instead of stealing a database directly, the attacker coaxes the model itself to divulge clues, a probability spike, a memorized phrase, or a pattern that reveals who or what was in the training data. Because the model is an artifact of training, privacy can be compromised during training, during inference, or across both through fine-tuning and updates. This makes privacy attacks distinct from general breaches such as network intrusions or lost laptops. Nothing leaves the system in an obvious way. What leaks is information embedded in parameters and outputs. Understanding this threat begins with a simple idea. Models do not just generalize patterns. They also sometimes memorize specifics. When memorization intersects with sensitive data, ordinary predictions can become a covert channel for disclosure. There are 4 canonical families of privacy attacks, each asking a different question about the data behind a model. Membership inference asks, was this exact record in the training set? Model inversion asks, given what the model outputs, what did the original input likely look like? Reconstruction seeks to rebuild large portions of the dataset by accumulating many small leaks over time. Attribute inference tries to guess hidden properties of an individual, such as a medical condition, by exploiting correlations learned during training. Although techniques differ, the fuel is similar: overfitting, spiky confidence scores, and correlations that tie outputs to identities. Think of these families as a map of adversarial curiosity, ranging from presence to content to context. Membership inference is the most direct line from output to privacy loss. The attacker submits queries, often the same example or a close variant, and watches the model's confidence, loss, or logits. Overfit models tend to respond more confidently to examples they have seen than to similar but unseen ones, creating a measurable gap. By calibrating decision thresholds on public or synthesized data, the attacker can classify an example as member or non-member. This can be done with black box access, meaning only the inputs and outputs are visible, or with white box signals when internals are exposed. Even simple classifiers can be vulnerable if trained on skewed or small datasets. The crux is that a yes or no about membership is itself sensitive, because presence in a dataset often implies something private. The implications of membership inference go beyond academic curiosity. If a model was trained on oncology records, confirming that someone's file was in the training set may reveal a cancer diagnosis. If a voice model includes recorded counseling sessions, membership could expose participation in therapy. Personal photo datasets, breach corpora, or financial ledgers carry similar risks, especially when the dataset captures stigmatized, regulated, or high-stakes contexts. Attackers can chain membership findings with public data to de-anonymize individuals or to target scams. Even noisy, probabilistic membership guesses can chill data sharing or participant trust. Critically, fine-tuning on small, sensitive sets common in practice can reintroduce overfitting and reopen membership channels, so risk is not a one-time event but an ongoing property of model lifecycle decisions. Model inversion asks the model to paint the person it remembers. Here, the attacker leverages outputs, probabilities, gradients, embeddings, or even text to synthesize an input that the model would strongly associate with a class or an individual. In computer vision, gradient-based methods can yield faces resembling those seen during training. The model's parameters act like a compressed gallery. In language tasks, inversion surfaces as verbatim regurgitation or near-verbatim reconstructions of passages the model absorbed. Especially rare strings like passwords, keys, or unique quotes. The central risk is that the model's internal representation contains enough detail to approximate private content. Even when the reconstruction is imperfect, it can reveal attributes, structure, or sensitive tokens. Inversion thrives when models are large, trained long, and lightly regularized, exactly the conditions that often maximize accuracy. Concrete scenarios make inversion tangible. An image classifier trained on hospital images may, under targeted optimization, produce a synthetic image that preserves identifying birthmarks or implants from a real patient. A face recognizer might yield a composite that allows a human adversary to pick the right person from social media. In text, an autoregressive model prompted with a distinctive prompt can spill a unique sentence from an internal memo or a snippet of a patient note if it was memorized during training. Even embeddings can leak. Nearest neighbor searches sometimes pull vectors that decode into rare phrases. These are not science fiction cases. They are natural consequences of models compressing data. Any system that rewards fidelity to training patterns must also police the boundary where fidelity becomes recall of specifics, and that boundary is surprisingly easy to cross. Reconstruction attacks scale leakage from anecdotes to archives. Rather than extracting one image or confirming one member, the adversary orchestrates many queries, each yielding a shard of information. With careful prompting, adaptive sampling, and error correction, those shards can be assembled into substantial parts of the original dataset: names, dates, templates, or even full records. Rate-limited interfaces do not fully solve this because patient attackers spread activity over time, devices, or accounts. Partial leaks, like rare templates in generated text or histogram-like outputs from analytics models, can be stitched together with auxiliary public datasets to fill gaps. The danger grows with repetition. Every deployment tutorial or demo becomes an additional opportunity to harvest crumbs. Sensitive collections, medical notes, educational records, internal chats are especially at risk because their language is patterned enough to be reconstructible but private enough that any reconstruction is harmful. The mechanics of reconstruction turn patients into power. An attacker might start by eliciting stereotyped templates, common salutations, boilerplate legal clauses, or progress note headers, then iteratively push for rarer fragments that complete those templates, such as names, dates of birth, or diagnosis codes. Each fragment is verified against public corpora or synthetic validators, and discrepancies feed back into smarter prompts. Over long horizons, the attacker rotates accounts, varies phrasing, and spaces queries to defeat rate limits and anomaly thresholds. Even privacy-preserving analytics can leak if they return fine-grained aggregates that are stable across repeated calls. Differences of differences can reveal small groups. Sensitive collections are appealing because they are internally consistent. School transcripts, case files, or clinical notes follow patterns that make missing pieces predictable. The result is not a single shocking leak but a slow accretion of facts that, when assembled, replicate material you never intended the model to reproduce. Attribute inference shifts the goal from "were you in the data" to "what hidden attribute applies to you." The attacker feeds observable features, age band, location, purchase history, phrasing style, and uses the model's outputs to sharpen a guess about a sensitive field the dataset contained but is not directly exposed. Correlations learned during training do the heavy lifting. Postal code and medication names can imply a diagnosis, vocabulary and timestamps can imply shift work, spending categories can imply income bracket. The process is probabilistic, but precision is not required to cause harm. A 70% confidence that someone is pregnant, immunocompromised, or in debt can trigger targeted ads, predatory offers, or social engineering. When models are deployed as decision aids, these inferences can even loop back into outcomes, quietly shaping opportunities or scrutiny without explicit disclosure. To mount these attacks, an adversary typically needs 4 ingredients. First, access to a query interface, public APIs, chat front ends, demo pages, or integration surfaces where inputs elicit informative outputs. Second, auxiliary knowledge that anchors guesses, leaked credential dumps, public records, social media, or open datasets that help disambiguate candidates. Third, computational power to run adaptive attacks, train shadow models, or optimize prompts. Today, modest cloud budgets or consumer GPUs suffice for many techniques. Fourth, persistence and organization, scripts to schedule queries, store intermediate signals, and iterate as defenses change. None of this requires elite capabilities. In fact, the same tooling used by developers logging frameworks, vector stores, evaluation harnesses, can be repurposed offensively. The asymmetry is sobering. A defender must sanitize every pathway, while an attacker needs only one reliably leaky channel to make progress. The individual-level consequences are concrete and personal. Loss of confidentiality is not abstract when a generated paragraph mirrors your clinical note, or a model's confidence spikes expose your presence in a sensitive registry. Health privacy can be compromised by inferred conditions or treatment histories, leading to stigma or insurance complications. Financial identities can be targeted through reconstructed account templates, recurring bill patterns, or inferred income ranges that guide spear phishing and fraud. Even when no single fact is definitive, the accumulation of plausible inferences erodes your ability to control how you are profiled. Trust suffers twice, first in the institution that collected the data, and second in the technology that promised helpful predictions but delivered leakage. People withdraw consent, withhold information, or avoid beneficial services when they fear that participation will echo back at them through a model. Organizations face system-level repercussions that quickly outstrip any single incident's scope. Regulatory penalties loom if protected health information or personally identifiable data can be inferred from outputs, even indirectly. Laws like the Health Insurance Portability and Accountability Act and the General Data Protection Regulation consider re-identification risks, not just explicit disclosures. Reputational harm compounds as examples circulate showing memorized lines or reconstructed forms, undermining narratives about responsible innovation. Partners and data providers become reluctant to share, stalling research and product improvements. Compliance programs buckle when audit trails cannot explain how particular outputs arose or why controls failed to prevent leakage. Most damaging privacy incidents tend to reveal deeper cultural problems: overcollection, just in case, weak data minimization, and a lack of privacy review at fine-tuning time. The corrective effort touches policies, pipelines, and people, not merely a patch to a single endpoint. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Detecting privacy attacks is hard because hostile queries often resemble ordinary use. A researcher testing edge cases, a developer debugging prompts, and an attacker probing for leakage can all produce similar input patterns. Outputs rarely confess a breach. Instead, the signals are subtle: slightly higher confidence on certain strings, unusual repetitiveness, or drift in perplexity. Ground truth is missing. You seldom know whether a particular answer used memorized content or legitimate generalization, so labels for detection models are scarce. Meanwhile, techniques evolve. Once you block verbatim prompts, adversaries paraphrase, randomize order, or split attacks across sessions. Effective detection layers multiple heuristics: temporal correlation of queries, entropy and repetition metrics on outputs, and cross-user pattern matching. Just as anti-fraud systems look for behavior, not a single transaction, privacy monitoring focuses on sequences and context. The goal is early suspicion and friction, not an impossibly perfect oracle. Regularization aims to lower the model's tendency to memorize, thereby shrinking the surface available to privacy attacks. Classic tools dropout, weight decay, label smoothing, and early stopping reduce overfitting by discouraging brittle reliance on idiosyncratic training examples. Noise injection can happen at several layers, to inputs, to hidden activations, or to gradients during training. Each method trades a small amount of accuracy on the training set for better generalization, which incidentally reduces leakage risk. Think of regularization as blurring the model's memory just enough that it recognizes patterns without recalling specifics. The design challenge is tuning these knobs per domain. Medical notes and legal text, for instance, benefit from stronger regularization than broad web corpora because the cost of memorization is higher. Combine these techniques with balanced datasets and stratified evaluation to avoid spiky confidences that power membership inference. Differential privacy gives mathematical shape to the intuition that no single participant should meaningfully change what a model reveals. In practice, differentially private stochastic gradient descent clips per example gradients and adds calibrated noise before updating parameters. The strength of protection is summarized by an epsilon budget. Lower epsilon means stronger privacy but more distortion. Proper accounting composes privacy loss across epochs and tasks, ensuring you do not overspend the budget during training or fine-tuning. The attraction is twofold: formal guarantees that apply even against adaptive adversaries, and an engineering workflow that integrates into existing training loops. The costs are real reduced utility at small data scales, and hyperparameters that are delicate to tune. But for high-risk domains, the trade is often justified. Adoption is growing in areas like telemetry learning and analytics, where organizations must learn from populations without exposing individuals. Access control turns privacy from a purely algorithmic problem into an operational one. Begin with strong authentication and per-tenant isolation so that queries are attributable and policies are enforceable. Rate limiting and burst controls reduce the feasibility of reconstruction by throttling adaptive sampling, while tiered allowances let low-risk users query more freely than anonymous traffic. Differential query privileges matter. Privileged staff might see richer explanations, but public endpoints return clipped or rounded outputs that leak less. Least privilege extends to data pathways around the model. Fine-tuning jobs, prompt repositories, and evaluation harnesses should each see only the minimum necessary context. Consider sensitive mode toggles that disable high-risk features, such as logit or gradient inspection outside trusted environments. Finally, rotate credentials, expire tokens quickly, and bind them to device fingerprints. Persistence is an attacker's ally, and access entropy is yours. Auditing closes the loop by turning raw logs into privacy intelligence. Track sequences of queries per identity and device, not just single calls, so you can spot adaptive strategies like boundary probing or combinatorial reconstruction. Measure output characteristics such as n-gram repetition, nearest neighbor overlap with known sensitive corpora, and abrupt changes in confidence that might indicate membership gaps. Rate analysis highlights slow and low attacks. Modest but sustained query volume against rare templates can be as revealing as noisy spikes. When incidents occur, reconstruct attacker sessions from immutable, time-synchronized logs to understand tactics and patch controls. Balance as essential logs themselves contain sensitive material, so apply retention limits, redaction and encryption, and gate analyst access behind just-in-time approvals. Over time, feed findings into automated playbooks that add friction in real time, CAPTCHA challenges, sandboxed responses, or temporary downgrades to privacy-hardened decoding. Encryption protects the channels and stores that surround your model so that leakage cannot be amplified by interception or theft. Transport layer security secures outputs in transit, while encryption at rest with disciplined key management prevents log scraping from becoming a secondary breach. Confidential inference running models inside hardware-backed secure enclaves reduces exposure of parameters and intermediate states to the host environment, limiting insider risks. Homomorphic encryption and secure multi-party computation enable computation on encrypted inputs, shrinking trust surfaces in collaborative analytics, though performance remains a consideration. Even simple measures help. Segregate logs by sensitivity, use write-only pipelines for high-risk outputs, and scrub prompts and responses of obvious identifiers before persistence. Encryption is not a silver bullet against model-level leakage, but it ensures that whatever the model does reveal is not further compromised by weak plumbing. Evaluating privacy risk starts with disciplined, empirical attack simulation rather than wishful thinking. Begin by mapping the most plausible adversaries and what they can touch: public endpoints, partner sandboxes, or internal tools. For each threat, script concrete tests, membership inference on stratified slices, inversion against rare classes, attribute inference on protected fields, using both black box and, where appropriate, white box assumptions. Hold out clean validation data so you can distinguish true memorization from lawful generalization. Compare outputs across model checkpoints and decoding settings to identify leakage-sensitive regimes. Treat this as an engineering experiment. Define success criteria, track confidence gaps and reconstruction fidelity, and record reproducibility details. The goal is not to prove absolute safety, but to surface where the model's behavior crosses a privacy line in your context, given your data sensitivity, your user promises, and your regulatory environment. A crisp threat model and repeatable harness make this work actionable. Quantification translates experiments into decisions you can defend. Establish risk scores that combine attack success rates with impact weights, giving more gravity to exposures of health, financial, or children's data. Where you use differentially private training, budget privacy loss explicitly, and track it like a first-class metric, alongside accuracy and latency. Add benchmark suites to continuous integration, small, curated sets that are maximally sensitive to memorization, plus canary synthetic records containing unique tokens that must never appear. Version your evaluation so model owners cannot cherry-pick favorable settings, and add drift monitors that alert when output repetitiveness or rare token rates change after a fine-tune. Most importantly, keep this loop alive. New data, new prompts, and new features change the leak profile. Schedule retests after material code changes and at fixed intervals, and publish simple dashboards, so product and privacy teams share the same, current picture of risk. Privacy risk is cross-sector, but the texture differs by domain. In healthcare, confidentiality is paramount because training data often encodes diagnoses, procedures, or clinician notes. Even probabilistic inferences can trigger obligations under the Health Insurance Portability and Accountability Act and related state protections. In financial services, reconstructed templates and transaction patterns enable fraud, discriminatory lending signals, or violations of the Gramm-Leach-Bliley Act safeguards. Academic research must balance openness with participant privacy. Models trained on thesis drafts or interview transcripts can jeopardize institutional review board commitments and undermine replicability. Government deployments add national security and civil liberty dimensions. Outputs might reveal investigative methods or allow re-identification of protected classes, contradicting statutory mandates. Across all sectors, vendor ecosystems complicate accountability. Models fine-tuned by partners or run on third-party platforms inherit upstream risks. Recognizing these sectoral nuances helps set thresholds, choose defenses, and communicate stakes to boards, regulators, and the public. Every privacy defense carries limitations that should be acknowledged plainly. Regularization reduces memorization but cannot prevent leakage when small, unique datasets are overrepresented during fine-tuning. Differential privacy provides rigorous guarantees, yet utility can degrade sharply at low epsilon on limited data, and misconfigured accounting nullifies protection. Access controls throttle adversaries but may also slow legitimate research and frustrate users, leading teams to create exceptions that reopen attack paths. Encryption secures channels and storage, not the semantics of model outputs. Operationally, defenses add computation, cost, and complexity, and these pressures tempt rollback during crunch time. Most of all, guarantees are incomplete because real deployments are messy. Logs drift from policy, redactions miss edge cases, and product pivots change incentives. Treat defenses as layers that shift probabilities, not absolutes. Combine them with governance, training, and culture so shortcuts are hard and privacy-respecting defaults are easy. Integrate privacy into the security lifecycle so safeguards accompany data from birth to retirement. At collection, practice data minimization, provenance tracking, and consent capture that specifies model uses, not just storage. During training, apply regularization tuned to sensitivity, consider differentially private optimization for high-risk corpora, and isolate fine-tune so small sensitive sets do not dominate gradients. At inference, constrain outputs with truncation, rounding, or template controls where appropriate, and design response policies that degrade gracefully when prompts look extractive. Post-deployment, monitor for leakage signals, rotate keys and tokens, and review logs with just-in-time access and automatic redaction. Embed privacy checks into change management and launch gates, with clear scoring thresholds that block releases when risk is high. When incidents occur, run privacy-specific playbooks and retrospectives, and feed lessons into your evaluation harness so the organization becomes measurably harder to exploit over time. This episode surveyed how privacy attacks exploit the boundary between learning patterns and recalling specifics. We defined the space membership inference, model inversion, reconstruction, and attribute inference, and explored the resources adversaries use and the harms they cause to individuals and organizations. We examined why detection is challenging, then walked through practical defenses: regularization, differential privacy, access control, auditing, and encryption, along with programmatic evaluation and cross-sector considerations. The central theme is discipline trade-offs. You can reduce leakage substantially, but you must measure, budget, and design for it throughout the lifecycle. As you proceed, keep privacy as a product requirement, not an afterthought, and communicate in terms stakeholders understand: risk scores, thresholds, and user promises. Next, we will build on this foundation with privacy-preserving techniques that let you learn from populations while rigorously limiting what can be learned about any individual. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.